Evening, everyone. My name is Nanga Catherine, a student at Makerere University doing software engineering. Today I'm going to be taking you through my project, and it is graph reasoning computational modeling for conception probability estimations using heterogeneous data. So the keywords of my project are conception probability prediction, knowledge graph reasoning, fertility, reproductive health, survival and casual modeling, heterogeneous biomedical data, and computational fertility. So, historically, fertility prediction relied on simple calendar methods or ovulation strips. So these approaches often failed to account for individual variability. With the rise of digital health and AI, we now have the opportunity to integrate clinical, lifestyle, and psycho-index data to build personalized interpretable models. This project aims to do exactly that. This table summarizes recent approaches to fertility prediction. While many models achieve decent performance, they often lack integration across modalities such as graph reasoning, temporal dynamics, and causal inference. Our work addresses these gaps by fusing mechanistic features, psycho-index sequences, and knowledge graph reasoning embedding into unified interpretable pipeline. The domain challenge is so clear. Traditional fertility tools don't reflect the complexity of real-world conception. And then computationally, we face the task of integrating diverse data types, mechanistic features, cycle sequences, and graph relationships into a unified model that's both accurate and interpretable. So our objectives focus on building a robust, interpretable AI system that integrates diverse data sources. And then the research questions guide our exploration into feature importance, model architecture, causal inference, and fairness, ensuring that our work is both technically rigorous and clinically meaningful. So the research contributions and outputs, our contributions, we built a graph temporal causal pipeline for conception prediction. We fused 5 graph embeddings. We modeled cycle-wise dynamics and estimated treatment effects. And then for the research output, we have a custom knowledge graph. Conceive Score is the name of our product. So our methodology, our system architecture, it begins with raw tabular and cycle-index data. We engineer mechanistic features and construct a heterogeneous knowledge graph. This graph feeds into RGCN and GAT, VGA, gene models to generate relational embeddings. We also apply a transformer to model temporal dynamics. So these outputs are fused either via late averaging or stacked meta-learners and passed into a causal inference layer for treatment effect estimation. So finally, we evaluate this performance and fairness using calibrated metrics. So this slide summarizes the mathematical backbone of our architecture. We use RGCN for relational graph reasoning, GAT for attention-weighted aggregation, and transformer for temporal encoding across cycles. So these embeddings are fused and passed into logistic regression or T-learner to estimate conception probability and treatment effects. So we curated 6 distinct data sets capturing demographic, hormonal, medical, physical, physiological, and prior history. So after preprocessing and alignment, we merged them into a unified data frame with 17 features. EDA revealed stable distribution and minimal missingness. setting a strong foundation for modeling. So this is our correlation heat map. And then the categorical variables, we plotted graphs of count versus the categories we had made from our data sets. And then this is our heterogeneous graph. So on this other side, it is zoomed. It is zoomed for you to see that it's per patient. It's per patient for all the number of patients we got from our data sets. Here we're going to be talking about our outcomes. So we modeled a light GBM, gradient boosting, and a temporal transformer. So we combined a temporal transformer for cycle level modeling, then a light GBM for tabular features with monotonic constraints and a meta model. So this meta model, a logistic regression meta model, it blends both of them. So the validation results showed improved calibration and discrimination, but test performance highlights the need for better generalization and fairness checks. So next, these are the results from all other models, the temporal models. So we evaluated these four unsupervised graph embeddings, RGCN, GAT, TGN, and GIN, for conception prediction using logistic regression across all models. The area under curve remained at 0.5, indicating no discriminative power. Meaning that none could distinguish between positive or negative outcomes. However, the F1 and precision scores were consistently moderate, suggesting that the models learned some structural regularities but lacked discriminative power. So this tells us that unsupervised graph reasoning alone is not enough. So to move forward, we'll need supervised graph training, richer temporal features. So next, I talked about us combining the embeddings from the 5 different models and then into a single 160-dimensional representation using late fusion. So when you look at the area under curve, it dropped to 0.42 on validation, and on test it dropped to 0.29. Next, these are the final validation results. As you can see, the nested cross validation, the area under curve is still 0.5, and then the time blocked validation, there's a slight drop in the calibration and ranking. So this from the last slide, this shows our model shows moderate performance during validation, but then it fails to generalize the unseen patients in the test set. So this suggests that it's learning some signal but overfitting the training distribution. So when we audit the calibration across the age and BMI quartile, we see clear subgroup variation. Older patients are well predicted, while others show distorted probability estimates. So this uneven calibration highlights the need for stronger regularization, and there's need for stronger regularization and temporal modeling to respect psychodynamics and fairness aware calibration strategies. Then the IPW model, it showed weak ranking ability and poor calibration, but maintained a decent F1 score. This suggests that it may be useful in binary decision settings, but requires a refinement for probabilistic tasks. And then the SHARP analysis, this group SHARP comparison shows how feature importance shifts across age groups. Progesterone is dominant in younger patients, while cycle-timing and BMI take precedence in older cohorts. So these insights support the need for age-aware modeling strategies. Model selection, we selected a graph temporal causal pipeline for deployment due to its interpretability, fairness, and clinical relevance. So the system architecture supports modular training, robust evaluation, and real-time prediction. So the interface is designed for both clinicians and patients, enabling actionable insights and ethical decision support. So this product here, it integrates graph reasoning, temporal modeling, and causal inference into a user-friendly interface. It's designed for both clinical and personal use. So every model has blind spots. So we've identified our limitations, and there are architectural limitations, data limitation, lifestyle feature imbalance, system level limitations. So each has a practical mitigation strategy. So these insights will help us in our next phase of refinement and deployment. The conclusions, we developed a graph temporal causal pipeline for conception prediction, graph reasoning, computational modeling, and then integrated mechanistic features, lifestyle factors, and psychodynamics to enhance interpretability. And in future, we hope to expand our database, verified on clinical outcomes and real treatment histories, and enhance our graph construction with richer relational metadata. These were the references we used. And then we would like to acknowledge the individuals, institutions, and organizations who supported us to make this research possible. Our academic mentors, the clinical collaborators. This work reflects a collaborative effort across disciplines, and we extend our sincere thanks to all of you. Thank you very much.